The last part of our project for this term is to try and tell a rock's story. And you guys have been given rock profiles that you need to work out the stories of. You were asked to pick one place in southeast Queensland to investigate and tell a story of. And then you were given a choice of 3 pictures of each of their profiles. Now let's have a quick look at them. Here is the Tweed Shield at Mount Warning. That's how it looks from space, and here is a rock profile of a cross-section of that area. And as you can see, there are many different rock layers that you need to investigate here. The Clarence Morton Basin runs across southeast Queensland here and is a source for an awful lot of our mining and water and groundwater. And its profile looks like this. As you can see, lots and lots of different types of rock layered down, and these funny little formations down here that we're about to learn about. And last but not least, the Glasshouse Mountains area where we live. Here is a picture of its cross-section. Now each one of these areas has a story, but in order to tell the story of the area you need to analyze and look at the rocks that are layered underneath that area, and not just look at the type of rocks, but look at their position, their shape, and look for any evidence of things that have happened to them in the past to tell us what happened to make them that way. Here are the principles that geologists assume when they're trying to understand some rock stories. Now these words are quite big. You don't need to remember the words. You just need to understand the original principles that they're about. And most of these you get already. Original horizontality. Basically, that means that when sediments are laid down, they tend to lie down horizontally on top of each other because of gravity. That's a pretty easy one for us to understand. And here's some pictures of that from our Sedimentary Rocks video. You can see the layers of sediment tend to lie on each other in a horizontal formation. The next principle is the one of superposition, which basically says that the layers on the bottom are going to be older than the layers on the top because things need to be layered on top of one another unless you've got evidence that something's been overturned. So again, back to our sedimentary rocks, we assume that these layers down the bottom here are a lot older than these layers up the top. It doesn't look like anything's been dug up or overturned or pushed and stuff. They're all horizontal, there's not a lot of bends or anything. So we assume these are older than these. The next principle is something called a cross-cutting relationship. And this is where you look at layers of the earth which have actually broken and slipped because they're not held together anymore. And here's a good picture to illustrate this. When you have sedimentary layers like this, because the crust moves, get breaks in those crusts, and because they're no longer cemented together, the movement can cause them to actually slip away or push up or push across. Now essentially these movements are caused when earthquakes occur. So you have breaks in the crust where the crust actually slips down or up or to the side, releasing a huge amount of energy at the time, and you can see that the crust no longer has layers that lines up, and we call these faults. Now these are evidence of what we call cross-cutting, okay, because we've cut through the crust. The next thing we have to look at is intrusive relationships. And this happens after cross-cutting occurs. I'll show you an example. Intrusions are when magma actually breaks up through the crust and goes through the layers and pushes up, if it reaches the top, forms a volcano. So when we see the hot spots of Hawaii or different volcanoes around the area, that's because magma has intruded or pushed up through the crust and come out the top and formed a volcano. And as it does that, it tends to also form layers as it pushes up through the crust. So we assume with intrusive relationships that this rock formed here is going to be younger than the layers it pushed through beforehand, because these layers had to be here before it pushed through to form that sort of a shape. Now if you look over here, we've got this sort of a formation here where it's actually gone out like this. Now notice this looks like a volcano. This is a laccolith. Notice how it looks like this volcano here. If it came up here and spread out, then that tells me that when this happened, this layer here wasn't here, that this was the actual top layer, and here's where it hit the atmosphere and it spread out, forming a tiny little volcano. So this also helps us to tell ages of when things happened. This is pushed up through here, and that's why it's got that nice thin tube, but when it hit here, it reached atmosphere or water, it could be water, you never know, and it's spread out. So this must be older than this layer here. So by actually looking and analysing rock profiles, we can not only tell what's happened, we can also tell the order that they happened in. They're the basic relationships that you need to remember when you're looking at a rock profile. Things normally form horizontally when the sediments are laid down. The bottom layer is older than the top layer. Faults or breaks in the crust can occur during earthquakes, and that those faults will then slip and the layers won't align anymore. And that rock that's igneous rock will actually intrude through the layers of sedimentary rock and cut through to form volcanoes, and that rock is actually going to be younger than the rock around it. So let's have a look and see if we can tell some